Hello students, today we are going to study the next synchronous serial protocol I2C protocol, or it is also called as I2C protocol. Its full form is Inter-Integrated Circuits Protocol. So before going to this protocol, let us see some things about the previous two protocols we have seen there for serial communication. The first one we have studied is UART, Universal Asynchronous Receiver Transmitter. So basically, we will see what are the disadvantages of UART and SPI, and then we will go to the I2C. So what are the disadvantages of UART? In UART, it is asynchronous communication. It means no clock data is transmitted. Devices must agree ahead of time on a data rate. So what happens in asynchronous communication? First, there must be uh, the data rate of transmitter and receiver must be matched. Okay, it means the two devices must also have clocks that are close to the same rate and will remain so. Excessive differences between clock rates on either end will cause the garbled data. It means the transmitter will transmit the proper data, but receiver will get a garbage data. Okay, so that is a possibility in asynchronous communication. Second part about the asynchronous communication is that asynchronous serial ports require hardware override. It means they require complicated hardware to perform that different start bit, adding the start bit, stop bit, and parity bit. So it requires hardware override. Then there is a bus contention problem. What is a bus contention problem? When two devices attempt to drive the same line at the same time, bus contention problem arises. Whom to give the access of the bus? That is called as bus contention problem. So these are the basic disadvantage of the UART communication. Then we will go for SPI, Serial Peripheral Interface. In serial peripheral interface, you are requiring 4 lines for connecting one peripheral to a controller. Means for one peripheral you have to spare 4 pins. And for every additional peripheral device, we are requiring one additional chip select signal there. Okay, means for every additional peripheral, we are requiring one IO pin, and hence as I go on increasing the peripheral devices in the system, more number of pins goes on increasing which are required for the system. Okay, and the second drawback, this is the first drawback of the SPI, and the second drawback of SPI is nothing but it allows only one controller on the bus. It is not allowing more than one controller on the bus. That is the second disadvantage of SPI. So for this, there is third protocol defined here, which is coming in between UART and SPI. Okay, so it will try to overcome the drawbacks of both the serial protocols. That protocol is nothing but I2C or I2C protocol, Inter-Integrated Circuit Protocol. It is a two-wire protocol. Means it is requiring less number of lines as compared to SPI. SPI requires 4 wire, but I2C requires 2 wire. But in case of UART, UART is also requiring 2 wires. But in case of UART, there is a mismatching of the data rate may occur there. Whereas in case of I2C, you are also giving serial clock also. So it's a synchronous protocol. So there is no case of mismatching of the rate. The clock is shared between the controller and the peripheral. Okay. So we will see this in detail. So this is there is one controller present there. One peripheral is present there. Between the controller and peripheral we can see that there is one line serial data line and the second line is the serial clock line interfaced between the two devices. Okay, so this is a two-wire protocol basically. SDA and SCL lines are present here. Another thing you can observe there is here more controllers are allowed there. So more than one controllers can be present in the circuit, more than one peripherals are also present in the circuit. So that is also another advantage of I2C. In case of SPI, only one controller is present there. In case of I2C, it can work with system where more than one controllers are present there. Okay. So let us see the details about the I2C protocol. I2C requires two wires. Two wires means it is working with only two pins. Okay, and so it is like a synchronous serial protocol. But those two wires can nowadays. Previously, it was only 127 devices were allowed to connect through I2C, but nowadays it can connect 1008 peripheral devices. Means with only two devices, two pins, you can connect 1000 different devices to the controller in the system. Okay. So that is the biggest advantage of I2C protocol. It is requiring very less hardware in the system. Then the second advantage of I2C is it is supporting multi-controller system. It means more than one microcontrollers can be present in the I2C protocol. You can communicate with more than one controllers in the system. It allowing more than one controller to communicate with all the peripheral devices on the bus. So this is another feature of I2C protocol. Then the third one, data rate. Data rates fall between asynchronous serial and SPI. So it is having the data rate greater than UART but less than SPI. So the typical data rates which are supported by I2C protocol are 100 kHz to 400 kHz. Okay. There is some overhead with I2C. For example, for every 8 bits of data to be sent, one extra bit of metadata, that is acknowledge or negative acknowledgement, must be transmitted. So that is a little overhead in I2C protocol, but it is uh, less as compared to UART. So how it works? Here it is working with two signals. One is SCL, serial clock signal, and second is SDA, serial data signal. So SDA is connected between all the devices. This is device 1, this is device 2, this is device 3. So three devices are connected with one serial clock line and one serial data line. Okay. So when you are connecting n number of devices in the system, you are still working with only two signals, serial clock and serial data. Another specialty of I2C protocol is that it is having open drain drivers. Open drain drivers means you can see that this is the output device. So this output device is not connected to the VCC internally. When no transistor or FET is connected to the VCC through any register internally, it is called as open drain drivers. Okay, so its drain is open there, or in case of BJT it's a collector. So in case of FET it is called as drain terminal. So its drain terminal is left open. Therefore these are called as open drain drivers. Okay, so it is having open drain drivers and pull up, and for connecting these open drain devices you need pull up registers at the output. So this is a pull up register. Okay, so these are open drain drivers present in the system. Okay, why do open drain drivers are used? The reason for using an open drain system is that there will be no chances of shorting, which might happen when one device tries to pull the line high and some other device tries to pull the line low. So if one device tries to make it high and other device tries to make the line low, then what will happen? Short circuit may happen and it will draw more current in the circuit. But when you are having the open drain drivers, you can directly short circuit many devices. It means the pins of many devices you can directly short, you can connect it to each other without shorting actually the VCC and ground. Okay, and for that it is using open drain drivers. Okay, then to connect these open drain drivers, it is using pull-up registers. Okay, any device on the I2C network can drive SDA and SCL low. Means these two lines, they can pull them to the low, but they cannot drive them high. Okay, means here pull-up register is required for each bus line. Okay, so what will happen when these are the pull-up registers connected to the lines. So for SDA line, one pull-up register is used, and for SCL, another pull-up register is used. What is the purpose of these registers? The purpose of these registers is to make these pins high. So by default, this voltage will be 5 volt. Okay, so they are pulling it to the high voltage whenever no other device is communicating with each other. That is the purpose of the pull-up register. So by default, it will make both SDA and SCL line high when no data communication occurs over I2C connection. Next, master and slave devices. Similar to the SPI in I2C, again you are having master and slave devices present. The devices connected to the I2C bus are categorized as either master or slaves. Okay, so what do you mean by master? Master means the controller present in the system, and slave means other peripheral devices. At any instant of time, so whenever there is a communication in the system using I2C, at any instant of time, only a single master stays active on the I2C bus. So at a time, only one master will be active there. Not more than one master will be active. And that will control the SCL clock, that is serial clock line for the I2C protocol, and decides what operation is to be done on the SDA data line. So in case of I2C protocol, the serial clock line is controlled by the master, and at a time only one master can stay active in the I2C bus. So similar to the SPI protocol, in I2C also you are having master and slave configuration. Means one controller will be active there as a master and number of other devices will be present there as slaves, or those peripherals are present there. Then how the I2C protocol is actually implemented there. Okay, so first, all the devices that respond to the instructions from this master device are called as slaves. Means will be one controller present there and different peripherals are present there. So the peripherals are called as slaves and controller is called as master. For differentiating between multiple slave devices. Now what is happening there? For one controller, multiple slaves will be present there. So the controller must identify which which slave I am currently addressing. So for that it is using address. A 7-bit address is used for each slave device. Okay, multiple slave devices connected to the same I2C bus. Each slave device is physically assigned a permanent 7-bit address. When a master device wants to transfer the data to or from a slave device, it specifies this particular slave device address on the SDA line, then proceeds with the transfer. So effectively, the communication takes place between the master device and a particular slave device. So what it is doing? Excuse me. It is giving the slave device address. So when it is giving the slave device address, the particular slave is identified, and it will communicate only with that particular slave device. All the other slave devices doesn't respond unless their address is specified by the master device on the SDA line. Means first the master has to identify the slave with its address, then only it will respond to the master. So here you can see one master device is connected and a number of slave devices are present here. And for every slave device, it is giving one unique address. And by giving that particular address, it will identify currently which slave it is communicating with. So for communicating with a particular device, it will use its particular address. Okay, in that way the master works with the slave. Now, how the data transfer takes place in I2C protocol? The data transfer between the master device and slave devices through a single SDA line is done, and it is done via patterned sequences of zeros and ones. So what do you mean by pattern sequences? So here the total sequence is given there. I will read the total sequence and I will explain all the sequences one by one. So the first part in the data transfer is start condition. The second part is 7-bit address, which is the slave address. It contains the address of the slave device. So for that it is containing the 7-bit address. Then read write bit. This is the third part. Acknowledgement or negative acknowledgement. Next is the database. 8-bit data bits are present there, and then 8-bit data bits are followed by acknowledgement or negative acknowledgement, and finally the stop condition. Okay, so this is the sequence. So total 6 different phases are present in the data transfer: start condition, address, read write bit, acknowledgement or negative acknowledgement, data bit, again acknowledgement or negative acknowledgement, and stop bit. So what is the first part? Start condition. So this is the start condition in the communication. Okay. Whenever a master device or IC decides to start a transaction, it switches the SDA line from high voltage level to a low voltage level before the SCL line switches from high to low. So what is SCL? Serial clock. Now serial clock must be high, and serial data line must have the transition from high to low. This is called as start condition for I2C protocol. Remember, I repeat it. For I2C protocol start condition, we are talking about the first part of the data transfer, start condition. In this start condition, serial clock is high and serial data line switches from high to low. This is called as start condition. Once a start condition is sent by the master device, all the slave devices get active. So whenever the start condition is sent by the master device, all the slave devices get active even if they are in sleep mode and wait for the address bits. Means they will come, though the peripheral devices or the slave devices are in sleep mode also, they will respond to the master, and what happen? They will wait for the address bits from the master. So this is called as start condition. The second is address block. Address block is having 7 bits, or in recent protocols it is 10 bits. So for 7 bits you are having the options of 128, and in case of 10-bit address you are having 1008 devices you can connect there. So there are different options present here, 7 bits or 10 bits. Okay, for 7 bit you are having 128. For 10 bits you are having 1008 devices connected in the system. It comprises, so address block, it comprises of 7 bits and are filled with the address of slave device to which the master device needs send or receive the data. All the slave devices on the I2C bus compare these address bits with their address, and they will decide whether the master is currently accessing that particular device or not. Okay, so for that it is sending the address block. So that is the second phase in case of the data transfer. Then the third one is read or write bit. This bit specifies the direction of the data transfer. If the master device or IC need to send the data to a slave device, this bit is set to 0. If the master IC needs to receive the data, so for reading it will be 1, for writing it will be 0. Read means to collect the data from the slave, write means to collect the data from the, to send the data to the slave. Okay, so from master to slave it is write, from slave to master it is read. So for that it is using read write this. Then the next part is acknowledge or negative acknowledgement. This is the next part, acknowledgement or negative acknowledgement bit. It's a single bit. Okay. It stands for acknowledged or not acknowledged bit. If the physical address of any slave device coincides with the address broadcasted by the master device, the value of this bit is set to 0 by the slave device. Otherwise, it remains at logic 1. Means, if the physical address of slave device coincides with the address broadcasted by the master, the value of this bit is set to 0 by the slave device. Otherwise, it remains at logic 1. So, it is giving the acknowledgement for the given address. So, if the address is matched, then it will set it 0. If the address is not matched, it will set it to 1. Then the next part is data block. So data block again consisting of 8 bits of the data. It comprises of 8 bits and they are set by the sender. With the data bits it needs to transfer to the receiver. This block is followed by an acknowledgement or negative acknowledgement bit and is set to 0 by the receiver if it successfully receives data. So this block is followed by an acknowledgement bit 0 if the receiver has successfully received data. Means acknowledgement bit is 0 and negative acknowledgement bit is 1. Otherwise, it stays at logic 1. This combination of data block followed by acknowledgement or negative acknowledgement bit is repeated. Remember, this is continuously repeated until the data is completely transferred. It means you can actually transfer n number of bytes using the I2C protocol. So you can transfer n number of bytes there using the I2C protocol, and until all the bytes are not transferred, it will not complete the data transfer. And for every byte, it will generate one acknowledgement or negative acknowledgement bit. So it is having self error checking bit, means whether the data is correctly received or not. That is given by these acknowledgement and negative acknowledgement bit. And the final one is stop condition. In the data transfer in I2C protocol, the last condition is a stop condition. Stop condition is exactly opposite of the start condition. So what happens in the start condition? When the SCL line is high, SDA line is having high to low transition. And in the stop condition, in the last condition, SCL line is high. Means this is high and SDA line is having the change from low to high transition. So rising gauge is present there, that is called as stop condition. After required data blocks are transferred through the SDA line, the master device switches the SDA line from low voltage level to high voltage level before the SCL line switches from high to low. So this is the final condition in the data transfer in I2C protocol. I will just repeat the 6 phases in the data transfer in the I2C protocol. First is the start condition, then the address bit, 7 bit, then the read write bit, and the last one is the next, it is followed by acknowledgement or negative acknowledgement. Then it is followed by 8-bit data bus. It is followed by acknowledgement or negative acknowledgement until all the bytes are not transferred, and finally it is stop condition. So in this way the data transfer takes place in I2C protocol. Now we will see, so this completes the 3 protocols which are used in the communication for the controller: UART, SPI and I2C. Universal Asynchronous Receiver Transmitter, Serial Peripheral Interface and Inter-Integrated Circuits. So finally we will see the comparison of these 3 protocols. So we will see one by one all the comparison points for all the 3 protocols. So the first one is, we will see the features UART, SPI and I2C. So the full form for UART, it is Universal Asynchronous Receiver Transmitter. For SPI it is Serial Peripheral Interface, and for I2C it is Inter-Integrated Circuit. How many pins are required for the UART? For the UART it is TXD, data transmit, and RXD, data receive. SCLK. For SPI it is serial clock, MOSI, master output, slave input, MISO, master input, slave output, and fourth one is slave select. So SCLK, MOSI, MISO and SS are the 4 pins required for SPI, and for I2C it is SDA, serial data, and SCL, serial clock. Now these are the interfacing diagrams for the 3 interfaces. In the UART, TXD is connected to the RXD and RXD is connected to the TXD. For SPI interface, MISO line of the master is connected to the MISO line of the slave. MOSI line of the master is connected to the MOSI line of the slave. SCK is connected to the SCK of the slave. And chip select is connected to the individual chip select signal of every slave. So this is the connection for SPI interface. And I2C is a 2-wire protocol. Only 2 wires are interfaced between all the devices present in the system. One is SDA, which is connected to the SDA pin, and the second is SCL, which is connected to every SCL present in the I2C interface. Then the next feature is distance. UART is used for very less distances, around 50 feet it is used. So UART serial communication is used for short distance communication only. SPI is used for the highest distance. So it is used for a very long distance communication, whereas I2C is in between UART and SPI. UART is asynchronous serial communication, SPI is a synchronous communication, and I2C is again the synchronous communication. Means both SPI and I2C will share the clock signal, serial clock signal. Then the number of masters present in the system. In UART, no masters is present in the system. In SPI, only one master is allowed there. In I2C, one or more than one masters are allowed. Clock signal. For UART, no common clock signal is used. Both the devices will use their independent clocks. In SPI, one common clock serial clock signal is present there between master and slave devices. For I2C, there is only one common clock signal is present between multiple masters and multiple slaves. Then the hardware complexity. In case of UART, the hardware complexity is very less. For SPI, it is less, and for I2C, it is more. Then how the protocol works for the three communications. For UART, the protocol is for 8 bits of data, one start bit and one stop bit is used. For SPI, there are different ways you can specify the protocol for different peripherals. But normally, in case of SPI, you are not giving the overheads there. Okay, because for every peripheral you are using the separate pins. So hardware goes on increasing, but as far as software is concerned, there is no any overhead present in the SPI protocol. Then the I2C. I2C uses start bit and stop bit, and it uses acknowledgement bit for each 8-bit data, of which indicates whether the data has been received or not. Means at the beginning of the transmission it will give the start bit, and at the end of the transmission it will give the stop bit. Means for whole number of bytes it will use only one start bit and one stop bit, as compared to UART, where for every byte it is using one start bit and stop bit. In case of I2C, it will, for n number of bytes, it will use only one start bit and one stop bit. Then, but it is using acknowledgement bit for every data byte. So there is some overhead present there. Number of masters we have seen there. Then software addressing. For your, as this is one-to-one connection between two devices, no addressing is present. In SPI, slave select lines are used to address a particular slave. So here you are using the slave select addressing. There will not be any software, that is address required for slave selection. So there will be n slave select lines on master device for n slaves. And finally the I2C, there will be multiple slaves and multiple masters, and all masters can communicate with all the slaves. Up to 27 slave devices can be connected or addressed in the I2C interface circuit. Advantages for the UART. It is simple communication. It is a simple communication and most popular, which is available due to UART supporting almost all the devices with 9-pin connector. And it is also referred as RS-232 interface. The advantage of SPI is it is simple protocol. It doesn't require processing overheads. It supports full duplex communication. Due to separate chip select line, same kind of multiple chips can be used in the circuit design. SPI uses push-pull and hence higher data rates and longer ranges are possible. SPI uses less power compared to I2C due to open collector design, and the next one is I2C. The advantage of I2C is due to open collector design, it is having limited slew rates can be achieved. More than one masters can be used in the electronic circuit design. Needs fewer wires, that is only 2 wires are required for communication. I2C addressing is simple, which does not require any chip select lines used in SPI, and it is easy to add extra devices in the bus. It uses open collector bus concept, hence there is bus voltage flexibility on the interface bus, and it uses flow control. Disadvantages for the UART. They are suitable for communication between only two devices. It supports fixed data rate agreed upon between devices initially before communication, otherwise data will be garbled. That is the biggest disadvantage of the UART. So if the baud rates are monotonous, the data will not be transmitted properly. And in case of SPI, the disadvantages, as number of slaves increases, number of chip select lines increases. It means hardware increases or hardware complexity increases. To add a device in SPI requires one to add extra chips like line and changes in software for particular device addressing is concerned. Means software is also increased. Master and slave relationship cannot be changed as usually done in I2C interface. So in case of I2C interface, you can easily change the master and slave relationship, but that is not possible in case of SPI. No flow control is available in the SPI. Another disadvantage of SPI. In case of I2C, it increases the complexity of the circuit when the number of slaves and masters increases. I2C interface is half duplex. It requires software stack to control the protocol and hence it needs some processing overheads on the microcontroller or microprocessor. So these are some comparison points of UART, SPI and I2C protocols. With this, we will complete the serial communication. Thank you students. Thank you one and all.